In the previous lesson, we studied how to graph and find parametric curves. Today we're going to do calculus with parametric curves. So the first thing is the parametric form of the derivative. So if you have a smooth curve C, and it's given by the equations x equals f of t and y equals g of t, then the slope of this curve C at xy is given by g prime over f prime, or dy dt over dx dt. And so I'll prove this in the case that we can eliminate the parameter. So if you can eliminate the parameter, you get some equation y equals capital F of x. And we know that y is equal to g of t, and x is equal to little f of t. So we have g of t equals capital F of little f of t. Now differentiate both sides and we'll have g prime of t is equal to capital F prime of f of t multiplied by f prime of t, or capital F prime of f of t is equal to g prime of t over f prime of t, which tells us that f prime of x is equal to g prime of t over f prime of t. So curve C is defined by the parametric equations x equals t squared and y equals t cubed minus 3t. Show that C has two tangents at 3, 0 and find their equation. So if we have the point 3, 0, we know that the x is 3. So we know that 3 is equal to t squared, which implies that t is equal to plus or minus root 3. And if t is equal to positive root 3, we know, or negative root 3, we know that x is equal to 3, and then we know that y is equal to 0 for both positive and negative root 3. So we have two tangents there. All we need to do now, because we have their x and y coordinates, is find their slope. So the slope of the tangent line is given by the derivative, which would be dy dt over dx dt. So dy dt is 3t squared minus 3, and dx dt is 2t. So we have 3 times t squared minus 1 over 2t. And if we plug in t equals positive root 3, we get that the slope is 3 times 3 minus 1 over 2 root 3. So that's a slope of 6 over 2 root 3. And if we rationalize that denominator, we end up with 6 root 3 over 6, or root 3. And in the other slope, we just plug in negative root 3, and we're going to get that the slope is also negative root 3. So the slope is, one slope is positive root 3, and one slope is negative root 3. And the equations of the lines are y minus 0 equals root 3 x minus 3, and y equals negative root 3 x minus 3. So you could say y equals plus or minus root 3 times x minus 3. So those are the equations of the two tangent lines at the point 3, 0. Find any points where the tangent is vertical or horizontal. So remember that our derivative, dy dt, or dy dx, is given by 3t squared minus 3 over 2t. So we have a vertical tangent if the denominator is 0, so 2t equals 0 implies that t equals 0, and that means that x is 0 and y is 0. And you get that by plugging t equals 0 into the parameterization. So if x is 0, y is 0, we have a vertical tangent at 0, 0. And we have a horizontal tangent if 3t squared minus 3 equals 0, which means that 3t squared equals 3, t squared is 1, so t is plus or minus 1. And if you input positive 1, we have the point 1 comma negative 2. And if we input negative 1, we'll have 1 comma positive 2. Now the second derivative is a little bit tricky. So recall that the first derivative, dy dx, is found by doing dy dt over dx dt. So the second derivative, d squared y over dx squared, is the derivative of the first derivative. And now this first derivative acts like the y does there. You see how it's sort of supposed to be there. So we'll find the second derivative by doing the d over dt with respect to t of the first derivative, all divided by dx dt. And we had that our first derivative, dy dx, was equal to 3t squared minus 3 over 2t. So the derivative of that is 3 over 2 times 1 plus 1 over t squared over dx dt, which is 2t. And that simplifies to 3/4 times t squared plus 1 over t cubed. And because the numerator is always positive, the concavity is determined by the denominator only. So we're concave up if t is positive, and we're concave down if t is negative. Next, let's sketch this curve. So let's start with making a table and inputting all the t's we have information about. So t, x, y. So we know that if t is negative 1, x is 1, and y is 2. We know that when t is equal to 0, the x and y are both 0. We know when t is positive 1, x is 1, and y is negative 2. And we also know that when t is positive root 3, the x is 3 and the y is 0. And when t is negative root 3, the x is 3 and the y is 0 again. So let's start. When t is negative 1, x is 1 and y is 2. And we also know that the curve is concave down at that point. And when t is negative root 3, x is 3 and y is 0. So we're kind of coming from back here when we're concave down. And then we go through the point 0, 0, and there's a vertical tangent. And then when t is 1, we go through the point 1, negative 2. We know that there's a horizontal tangent at the point 1, 2, and at 1, negative 2. Then we go back through that point, and we're concave up forever. So roughly speaking, there is a picture of the curve C. Next, let's do the same thing for a specific cycloid. So given the cycloid, x equals 4 times theta minus sine theta, and y equals 4 times 1 minus cosine theta, find the following. So first, find the tangent of the cycloid at theta equals pi 6. So the derivative tells us the slope. So that will be dy d theta over dx d theta. So dy d theta will be 4 sine theta. Dx d theta will be 4 times 1 minus cosine theta, which simplifies to sine theta over 1 minus cosine of theta. And at pi over 6, we'll have that the slope is sine of pi 6 over 1 minus cosine of pi 6. So sine of pi 6 is 1/2. Cosine of pi 6 is root 3 over 2, which simplifies slightly to 1 over 2 minus root 3. That's the slope. We need to find the point. So the x-coordinate is 4 times pi 6 minus sine of pi 6. Sine of pi 6 is 1/2. So 4 times pi 6 minus 1/2, which is at best 2 pi over 3 minus 2 eeg. And then the y is 4 times 1 minus cosine of pi 6, which is root 3 over 2. So 4 times 1 minus root 3 over 2, which is 4 minus 2 root 3. So an equation of the tangent line is y minus the quantity, 4 minus 2 root 3, equals 1 over 2 minus root 3 times x minus the quantity, 2 pi thirds minus 2. Ugh. Don't graph that. Find the points at which the tangent is horizontal. So we have that the derivative dy dx is equal to sine theta over 1 minus cosine theta. And the tangent line is horizontal if sine theta is equal to 0, but 1 minus cosine theta is not equal to 0, meaning cosine of theta cannot equal 1. And so this occurs at all, when theta is equal to all odd pi's. So whenever you input an odd pi for theta, you will have a horizontal tangent. And let's use this to sketch the cycloid. So we'll make a table with theta, x, and y. Now if theta is 0, sine of 0 is 0, we'll have x is 0, cosine of 0 is 1, y is 0. So we start at the point 0, 0. Now if we plug in pi, sine of pi is 0, so x will be 4 pi, and y will be 8. And because we input an odd pi for theta, we know that the tangent is horizontal there. Next, let's plug in 2 pi. In that case, the x is 8 pi, and the y is 0. And then if we plug in 3 pi, the x is 12 pi, and the y is once again 8. And by 16 pi, we're back at 0. And that pattern just continues out in either direction. Now notice with this cycloid that it's the case that you go through one arch when you have gone from 0 to 2 pi. And this distance is 2 pi times 4, where 4 is that number in front there. So had we had just r, it would have been 2 pi r. Next, let's find areas. So the area under a curve y equals f of x from a to b is given by the integral from a to b f of x dx, provided that your function f of x is bigger than 0. And if the curve is traced once by the parametric equations, x equals f of t, g equals t for t's between alpha and beta, then instead of thinking about f of x as y, you can use the g of t equation for y, and dx is the derivative of x, or f prime. So let's use this to find the area under one arc of the cycloid. So first recall that from that earlier example that the arc goes from x equals 0 to 2 pi r. So the area is equal to an integral from 0 to 2 pi r y dx. And this 2 pi r corresponded to theta being 2 pi. So this becomes an integral from 0 to 2 pi. Y is the equation r times 1 minus cosine of theta. And dx is the derivative of this one, which will be r times 1 minus cosine theta d theta. Which when we factor out those r's, we get r squared. And then expand, we'll have 1 minus 2 cosine of theta plus cosine squared of theta. And then expand the cosine squared using your double angle identities from the lesson we did with integration. So 1 minus 2 cosine theta plus 1/2 times 1 plus cosine of 2 theta, which simplifies down to r squared times the integral from 0 to 2 pi, 3 over 2 minus 2 cosine theta plus 1/2 cosine of 2 theta d theta. Now if we anti-differentiate, we'll have r squared times 3 over 2 theta minus 2 sine of theta plus 1/4 sine 2 theta, evaluated from 0 to 2 pi. And when you input 2 pi and 0, sine of 2 pi and sine of 4 pi as well as sine of 0 are all 0. So what we're going to end up with here is r squared times 3 over 2 times 2 pi, which is 3r squared pi. So the area under one arc of the cycloid is given by 3r squared pi. As parametric equations can be used to describe the path of a particle, finding the arc length would give you a method of finding the distance traveled by a particle along its path. So here is the arc length formula in parametric form. So the integral from a to b of dx dt squared plus dy dt squared, or the integral from a to b of f prime of t squared plus g prime of t squared dt. And notice that a and b in this case have to be bounds on t. And here is where that comes from. So the regular arc length formula is the integral from a to b root 1 plus dy over dx squared dx. And suppose we change that from alpha to beta, and we have 1 plus dy dt over dx dt, that quantity squared, and then times dx dt dt. So that's the same thing, and then simplifying a little bit, we have the integral from alpha to beta root dx dt squared plus dy dt squared all over dx dt, the quantity squared, times dx dt dt. And when I factor this dx dt squared out and root it, it will cancel with this one, which gives us the formula that we have here. So those probably should say alphas and betas as opposed to a's and b's. So are there bounds on the, well, I guess it does say t is between a and b, but to distinguish between x values in the proof we use alphas and betas. And so that can make a lot of these arc length problems a little bit simpler. So prove that the circumference of a circle is c equals 2 pi r. When you asked about this in like the 3rd grade, no one told you that. Proving that this was true actually required calculus. So recall that the parameterization of a circle of radius r is given by x equals r cosine of theta and y equals r sine of theta for theta between 0 and 2 pi. So the length of the curve will be given by an integral from 0 to 2 pi dx dt squared plus dy dt squared, the quantity square rooted, dt. So 0 to 2 pi dx dt squared, so dx dt would be negative r sine of theta squared, dy dt would be r cosine of theta squared dt. So that's the integral from 0 to 2 pi r squared sine squared theta plus r squared cosine squared theta. And if we factor out the r squared and root it, we'll have r times the integral from 0 to 2 pi of the root of sine squared theta plus cosine squared theta d theta. And sine squared theta plus cosine squared theta is 1. So we have the integral r times the integral 0 to 2 pi of 1 d theta. Super easy. R times theta from 0 to 2 pi, which gives us 2 pi r, as promised. Next, let's find the length of one arc of the cycloid. So the length will be given by an integral from 0 to 2 pi because one arc is traced in 2 pi radians. So we have that dx dt is equal to r times 1 minus cosine of theta, and dy dt is equal to r sine theta. So when we input those and square them, we'll have r squared times 1 minus cosine of theta, the quantity squared, plus r squared sine squared theta d theta. So factor out that r squared and root it, and we'll have an r out in front, 0 to 2 pi, and expand 1 minus 2 cosine of theta plus cosine squared theta plus sine squared theta d theta, and that cosine squared plus sine squared is equal to 1. So we'll have r integral 0 to 2 pi root 2 minus 2 cosine of theta d theta or 0 to 2 pi 2 times 1 minus cosine of theta d theta. And here's where it gets a little bit tricky. Remember that we knew that sine squared of theta is equal to 1/2 1 minus cosine 2 theta. So if we solve that for the cosine, we have 2 sine squared theta equals 1 minus cosine of 2 theta, or cosine of 2 theta is equal to 1 minus, oh, that's good enough. Okay, so we got that there. All right. So 1 minus cosine of 2 theta. Now what you have here is 1 minus cosine of theta. So notice that this angle, the relationship between this angle and that angle. So if inside the cosine you have 2 theta, inside the sine is theta. So if I have 1 minus cosine of theta, that would equal 2 sine squared of theta over 2. So I can replace this 1 minus cosine theta with 2 sine squared theta over 2. And that's really, really tricky. So that won't happen on a quiz, or that will not happen on a test. 2 times 2 sine squared theta over 2 d theta. So that's 2r integral from 0 to 2 pi of just sine of theta over 2 d theta. And now it's something that you can actually integrate. I mean, that trigonometric manipulation is pretty darn tricky, and it's hard, unless you've done a lot of that recently, to catch all those tricks and to see every single little thing you can switch. But now we can integrate this. So we have 2r, the antiderivative of sine is negative cosine, theta over 2, multiplied by 2, actually. So from 0 to 2 pi. So we'll have 4r negative cosine of pi plus cosine of 0. Cosine of pi is negative 1, so double negative makes it positive. So we have 4r times 2, or 8r. So the length of one arc of the cycloid is 8r. A circle of radius 1 rolls around the circumference of a larger circle of radius 4. The epicycloid traced by a point on the circumference of the smaller circle is given by these equations. Find the distance traveled by the point in one complete trip around the larger circle. This ends up producing something that looks kind of like a flower. So you have a circle of radius 4, and another circle that spins around it, and it produces this sort of like 4-petal flowery shape. And of course you're dying to find out the length of the flower. Sorry, no, you're not. Alright, but the length of that flower will be given by just one of those petals times 4. So 4 times the integral from 0 to pi halves, because we went from an angle of 0 to pi halves, root dx dt squared plus dy dt squared dt. So that'll be 4 times the integral from 0 to pi over 2. So dx dt will be negative 5 sine t plus 5 sine 5t squared. And then plus dy dt, so the derivative of 5 sine t is 5 cosine t. So 5 cosine t minus 5 cosine 5t, that quantity squared. And now icky algebra happens. So if I ask you these questions on quizzes or tests, I'm probably just going to say set up, do not solve, or I'll pick stuff that's a lot easier. So expanding this out, we'll have 25 sine squared t minus 50 sine t sine 5t plus 25 sine squared 5t. This is expanding out the first thing in parentheses. And then plus 25 cosine squared of t minus 50 cosine t cosine 5t, and then plus 25 cosine squared 5t. Hoofda. Okay, now what we can do first of all is factor out a 25, which would give us outside the integral 4 times 5, or 20. Okay, good. Got that much. 0 to 2 pi over 2. Now, inside the root, this sine squared plus that cosine squared is 1. And this sine squared plus that cosine squared is also 1 because the angles inside match. And then the other portion we have is minus 2 times sine t sine 5t plus cosine t cosine 5t. So simplifying slightly, we have 20 times the integral from 0 to pi over 2 root 2 minus 2 times sine t sine 5t plus cosine t cosine 5t. And what you do now is apply these sum difference identities from trig to conclude that this is actually equal to cosine of 4t. That's so tricky, so ridiculously tricky. So we have 20 times the integral from 0 to pi over 2 root 2 times 1 minus cosine of 4t. And as if that first trick wasn't enough, you also have to change this into 2 sine squared of 2t. I'm so sorry. So we have 20 times the integral from 0 to pi over 2 root 4 sine squared 2t dt. So that's 40 times the integral from 0 to pi over 2 sine of 2t dt. Ugh. Yuck. So 40 times negative 1/2 cosine of 2t, which will be 40 times, when you plug in pi halves, we have cosine of pi, which is negative 1, so 1/2 minus negative 1/2, so plus 1/2. This is equal to 40. Arc length is just ugly in general. So here's a pretty good application to a manufacturing question. A thin sheet of metal that is 0.1 inches thick is wound around an inner reel whose inner radius is 1 and whose outer radius is 12 inches. How much metal is required to fill the reel? So like how long would that piece have to be? So what we're going to start with saying is that the distance from the center that's going to increase linearly at 0.1 inches per revolution. So that tells us that the radius is equal to 0.1 times theta over 2 pi. And since 0.1 is 1/10, it's theta over 20 pi. And we have that x is equal to r cos theta, or theta over 20 pi times cosine theta, and y is equal to r sine theta, which is theta over 20 times 20 pi times sine theta. And what we have to figure out is, when does this start? So at which theta do we start at? So if r is equal to 1, this implies we have 1 equals theta over 20 pi. So the first angle I have is 20 pi. And if r is equal to 12, 12 is equal to theta over 20 pi. So theta is equal to 240 pi. So the total length of this curve is given by an integral from 20 pi to 240 pi dx d theta squared plus dy d theta squared d theta. And you have to use the product rule to differentiate everything here. So we have the integral from 20 pi to 240 pi root negative theta sine theta plus cosine theta all over 20 pi, that quantity squared, plus, if you differentiate the y using the product rule, you'll have theta cosine of theta plus sine of theta, the whole thing squared over 20 pi d theta. Now, the over 20 pi can be squared, factor out of the root, get square rooted, and the stuff inside the parentheses, when you expand and simplify, you actually end up getting theta squared plus 1. If you want to convince yourself, go ahead and do that, but trust me, that's actually what happened. So what we have now is 1 over 20 pi times the integral from 20 pi to 240 pi root theta squared plus 1 d theta. And it looks so simple, but it requires a trig substitution, and we're not going to go into that because it's just super tedious. So I will say in life you use a calculator, and you probably use a calculator at the point at which you, even before you simplified this stuff. There is a table that tells you what this integral is. It's 1/2 times theta root theta squared plus 1 plus the natural log of the absolute value of theta plus the root theta squared plus 1. Yuck. Again, 0, 20 pi to 240 pi, and it's about equal to 4,492.5 inches. I'm so sorry for all the tedium. I just wanted to give you an example of something that actually did kind of apply to life. I guess the lesson is that life is complicated. So the final application we will have is to the area of a surface of revolution. So if your surface is revolved around the x-axis, you will take the integral from 2 pi times the integral from a to b g of t times this. Notice that this is the same thing for the arc length. How I would think about that is this, is you have some curve, 2 pi y would find the circumference, that's what this 2 pi g of t is, times the little bitty length, which is given by that formula. So that's why the x-axis has the g of t. If you have the y-axis, so sideways curve, circumference, 2 pi, in this case x is f of t, and then times the little bitty length, which did not change. So let's use that. We're going to find the arc. We have c, our curve is the arc of the circle, x squared plus y squared equals 25, from 5, 0, so 5, 0, to 5 halves 5 root 3 over 2. So that arc of the circle. And I want to rotate this arc, it's a very bad looking arc, about the x-axis. So first of all, what I have to do, so if I have a circle of radius 5, x will equal 5 cosine of theta, and y is 5 sine of theta. That's just the typical parameterization of a circle of radius 5. And it's pretty obvious that 5, 0 corresponds to theta being 0, but 5 over 2, okay, so that's the x-coordinate. So if 5 over 2 equals 5 cosine of theta, it's like saying 1/2 equals cosine of theta, and that happens at theta equals pi thirds. So my surface area is given by rotation about the x-axis, so 2 pi integral from 0 to pi thirds, so 2 pi g, which was the y, 5 sine of theta, times the root of negative 5 sine theta squared plus 5 cosine theta quantity squared d theta. So that will actually be 10 pi times the integral from 0 to pi thirds of sine of theta times 5. And that's because this really is 25 sine squared theta plus 25 cosine squared theta. When you factor out the 25, it roots to 5, and then sine squared plus cosine squared is 1. Whew, thank God, something easy. So now we have 50 pi. The antiderivative of sine is negative cosine from 0 to pi thirds. So 50 pi. So at pi thirds, cosine is 1/2. So we'll have negative 1/2 plus 1. So it's like this has area 25 pi. And the last thing we will do is prove that the surface area of a sphere of radius r is 4 pi r squared. So once again, we have x is equal to r cosine theta, it's just that r is r instead of 5, and y is equal to r sine theta. And we're going to rotate this semicircle about the x-axis. And notice that corresponds from angles going from 0 to pi. So the surface area will be given by 2 pi, integral from 0 to pi, so 2 pi y, so r sine theta, times the root of dx dt squared plus dy dt squared, so dx dt is negative r sine theta quantity squared plus r cosine theta quantity squared d theta, which will be 2 pi integral from 0 to pi, actually that r can factor out, sine of theta times r. Because once again, inside the square root sign, we have r squared sine squared theta plus r squared cosine squared theta, much like the last example with the 5. The r squared can factor out, it roots to r. We're left with sine squared plus cosine squared, which is 1. So now we have 2 pi r squared. The antiderivative of sine is negative cosine from 0 to pi. So when we plug in pi, we'll get negative negative 1, so negative negative 1, plus cosine of 0, which is 1. So we get 4 pi r squared. And now your life is complete, because you know how to prove the surface area of a sphere is 4 pi r squared, and the circumference of a circle is 2 pi r, and all those things now make sense.